Let's go ahead and get started. Welcome back. Where we left off on Friday, we were just introducing kind of the most fundamental looping structure, the repetition structure of the while loop. And syntactically, there isn't that much new here, right? It looks very similar to our if statements. The implication is different. Instead of just making a single decision, we're making the same decision over and over and over again and deciding whether or not to continue inside that loop or to allow control to continue past the end of that loop. This slide where we left off on Friday was an example of a so-called infinite loop, a loop for which we have set up some condition inside the while statement that should, at least in theory or by intention, allow us to eventually exit that loop. But due to some bug or in our logic or in our implementation, we don't actually ever hit that condition. This example, like a lot of our in-class examples, very synthetic. So we set up a value called a, that's our sentinel value, that's what we're checking each time through the while loop. We're adding 2 to that value of a, so a goes from 1, 3, 5, 7, 9. And just for purposes of setting up this example, our condition for which we would then exit the while loop is a not equal to 20. Well, if a is odd and we keep adding 2 to it, it'll never actually be equal to 20. So we're going to stay inside that loop indefinitely or infinitely. And then when we refer to something as an infinite loop, that's what that means. It's a loop that we enter that we never actually exit out of. This example is synthetic, as I mentioned. It's actually quite easy to do that in your code. And all it takes is just one little logic bug, right? The same kind of logic bugs that in our if statements, it just doesn't execute the code we hope it would. If you have the same exact type of logic bug in your while loops, you could very likely have either a loop that never iterates, even though you expect it to, or a loop that continuously, infinitely iterates, even though you eventually do want it to end here. I think why it's worth spending a little bit more time, even though this example is pretty synthetic, on the example, is because it's important to develop a couple strategies for both determining that you have an infinite loop and also how one can debug exactly what is happening here. By default, if you have an infinite loop, of course it depends on the nature of the loop and what the loop is doing, but you're in Replit, you wrote a while loop, you're going to test it, and it just gives you kind of the impression that something's wrong, right? I hit the run button and by default, nothing seems to be happening. There is a tab where you can monitor that the CPU is actually working. It is doing something, but that doesn't really give you too much feedback that something is going on. But that is what's happening here. It is executing. It is inside lines 6 through 9 here in the code. It just there's no visible output, and so you're running it. You're not really sure how long your program should be taking to run. You could be sitting there and wasting 10 minutes and not realizing that this isn't going to work. It's not doing what you would expect it to or what you were expecting it to do. A very common approach as your programs get more complex is to add these little, and I call them sanity checks. That's just my term for it. Just little printfs beyond just the ones we already use for debugging purposes of here's the value of my variable. Just little printfs that just kind of confirm that, hey, I got to where I think my program should be getting to. It doesn't have to be really eloquent because it's a very temporary thing. Something like got here, or which is really shorthand for reached this point in the program. If you want to write it out really eloquently, you can. But for me, because this is very temporary, just to confirm that something's going on. Hey, did my program ever get to line 6? Okay, in this program, it certainly should. But as your programs get more complicated, and this is just one small part of a much larger program you're working on, and you know something's wrong, but you're not quite sure what, this is a good little sanity check. Hey, got here, maybe I want to do like got here 1 or got here 2 to kind of disambiguate which one is which. That does give you some additional piece of feedback. Okay, should print out got here 1, but hey, it never printed got here 2. That's at least a hint what happened, right? Okay, we got to line 6, but we never got to line 11 in my program. And so something in between those 2 lines is the problem. I know in this case it's obvious. Later on, that's just a good little thing to add. Okay, something went wrong. my program isn't doing what I think it's doing, it's not entering the function I created, or it's not going into the loop, or it's not taking the branch I really do expect it to take, that is a good starting point. That gives us a hint. There is, and it's somewhat compiler dependent, but it would work for our purposes. You can actually be more specific and say, reached line number and then %d, where there's a macro built in where you can specify, and it'll actually print out, I said reaching, I would say something like reached, because we have reached it, and that'll print out the actual line number for wherever that line of code happens to be in your program. That can also be useful. You can do things like I'm in this function or in this file, in similar mechanisms. Depending on how many of those debug sanity checks you need to add, that could be a useful thing to add to your program. But the very basic got here is also probably going to be sufficient for determining that, yes, I do have an infinite loop. Okay, perhaps we look at this loop and it's obvious that, well, yeah, that's a bug. We can fix that, or we could change the code to do something slightly different, but it's not always going to be obvious. And the next step, the next mechanism I would suggest for you then to add to your loop bodies would be that debug printf of, okay, I know A is the critical variable here. We may want to print out a whole bunch of our variables, not just A, but at the very least, I think it would make sense when we know something is wrong with our loop control variable, let's check what that value of A is as we go here. That will help to some extent. I hit run with the left mouse, and we see A is just blasting off, right? A is just going on, not indefinitely. Eventually it's going to overflow like we've seen, but that will take quite a while with a 32-bit integer to eventually overflow. This should tell you something, right? When you see, okay, I printed out this little printf of the variable, and it's just going nonstop. Okay, that's a pretty strong hint again that you have an infinite loop. We had a good idea already because we never reached that line 12 that, yes, this was probably an infinite loop. Part of the problem with that simple printf, in my opinion, is, again, in this example, we know the value of 20 is what's relevant, but in more complicated examples, it won't be that obvious, like why did the loop not stop when we thought it was going to stop? But in this case, then when we print it out, before we know it, we have a value of A in the multiple thousands, and we kind of skipped over or just went too quickly the part that's actually very relevant to where our bug is in our code. Oftentimes, what you will then want to do next is, okay, I have a good reason to believe I got to line 6, but never to line 12. Something is clearly wrong with A. For me, the next step would be, let's actually slow this down a bit. There's a lot of different ways you can slow down the execution of your function. One such function you can add is just called sleep, where sleep takes as input a number of seconds that the code is going to just effectively pause. It's unhappy about the definition of it because it's not in standard.io.h, it's in another header file that's part of the C standard. So if you include unistandard.h, you can call sleep. It probably would have worked anyway. Now I'm going to do the same printout, and then I'm going to wait for a second each time. And a second oftentimes is enough time to sleep to say, okay, all right, expecting A to be equal to 20. Oh, that's right. A is not actually ever equal to 20. It jumps right over 20. I know, again, for this example, it's obvious when we look at it that that's what happened. But now it's going nice and slow, and it's giving us more kind of, visible feedback as to what is happening with our variables as we're running these, multiple iterations of our program. Other approaches, there's nothing wrong with sleep. That's a good way to do that. If you really want to literally pause, there's a function we don't use for too much else these days called getCharacter. Grab a single character from the input. You could use scanf for this as well. And that basically stops things until you enter in a character. It's entering 2 characters at a time because I'm pressing enter as well. But that at least allows you to manually just kind of pause things and run it at the rate that you feel comfortable analyzing the execution of your program. There are more formal ways to do this. You can execute using a debugger. You can insert breakpoints where you say, I want to stop on this line of code until I tell you to continue. There's nothing wrong with doing that. This approach, where it's a combination of either sleeping or scanf, reading in a character, is probably going to be sufficient for our purposes. So this bug will happen to you many times this semester. Whether it's an infinite loop or it's just code that you think should be running that is not running, things just being stuck. Those kind of sanity check printfs, debugging of your variable print statements, and then oftentimes, certainly if it's part of a loop, slowing things down is going to be your starting point for figuring out why are things not working for me. Questions about this example?
When you go over the use of jar.
Yeah, this is a function that reads in a character from the input. So it's like scanf. The equivalent of this call would be something like this. You could also have done it. You could also have done it this way. It's equivalent to calling scanf on a single character. And we'll leave that there so you can look at that later. That's just a way, because that's a blocking I/O call where with all of our scanfs we've seen, the code will just not continue. The program will not continue until you enter in something for that scanf. That's a way to just freeze the execution of your program until you're ready to continue, and then it'll continue to the next iteration. That's if sleep 1 isn't enough time to sleep and we really want to slow things down and really stare at all of our data, then go to the next iteration. Then stare at all our data, then go to the next iteration. Really depends on what you're trying to debug. Sleep is oftentimes sufficient, but freezing things completely is oftentimes a very valid thing to do as well. Small aside, and this is something you never strictly need to do, it's extremely common to have these assignment statements that update a given variable's value. Like in this previous example, we had a equals a plus 2. You'll see in other code that you're writing or other code that you're reading that that's such a common thing. There's a compound assignment operator that just slightly simplifies those expressions. So for any of the operators that we have defined, if it is the variable itself that we are updating, so it is both on the right-hand side of the equal assignment operator and on the left-hand side, then you can actually just use the compound assignment operator instead. And I don't really have that much more to say other than that this is just an equivalent way to write it. If it's a equals a plus 2, you can also just write a plus equals 2, and that's what that means. And I don't know if we've done that so far this semester, but it is equivalent. And for both of these, for both the sum variable and for the a variable, if you're both reading and writing from the same value in that assignment operator, you don't really need to write it out as explicitly. There was a time when saving keystrokes and saving bytes of storage of our programs was a consideration, and maybe that's the genesis for that little shortcut operator, but that's really all that it's there for. It's the same exact operation. It's not faster or better or anything along those lines, but you'll see that enough that it's at least important to be aware of that that's what that means. A plus equals 2 means take the value of A, add 2 to it, update the value of A from that same line of code. Just like with if statements that we've already covered, loops just need to become part of your problem-solving process. There's only so much you can do with programs without having loops. When we're given a task to solve, the first question you want to ask yourself is there some task, subtask that is going to need to be repeated a given number of times? Usually for anything, beyond a bare minimum of complexity and level of interesting challenge to the problem, the answer is going to be yes to that. There's going to be some repetition. I'm going to need to do something multiple times in a row. The second question you then answer, you want to ask yourself as you're going through the problem-solving process, do I know in advance how much repetition there is? Is it a fixed number of things that I am doing here? When using while loop, I've written this a little bit backwards here. When using while loops, the answer is usually not. Let me then rephrase that the more correct way. If you don't know exactly how many times it's going to loop, then the while loop is the appropriate construct to use here. I know I need to loop a bunch of times. I don't know exactly how many times, but I do know I'm going to need to loop until some condition is met, for example. That's when we want to use the while loop. In just a couple minutes here, we'll learn the for loop if you haven't already experienced it and encountered it. The for loop usually makes more sense when we know there's a very specific, concrete number of times I want to loop. I want to do something 74 times. And I know that as part of the problem that I'm trying to solve, I want to do this code 74 times. Then a for loop is going to be the right construct for us, because you could do it with a while loop, but the for loop is a much more natural way to do it. And then the third question you always have to ask is, how will I know when to stop looping? I know I need to loop. I'm not necessarily sure how many times I need to loop, so I'm going to use a while loop, but I need to have some way of determining when am I going to be stopping? When is the appropriate time to stop looping? It's going to always be based on some value, some variable's value. Sometimes it's a quantifiable value for which we know when this value of max or sum or iteration count is greater than 293, then we're going to stop our looping. Other times it's not so clear. It's, well, when the user types in quit, then I want to stop looping. So what we do then tend to have for that nature of loops is to set up a separate variable, an explicit separate variable referred to as a sentinel value, that variable's only purpose is to determine when to exit the loop. Those of you who finished that supermarket example in which the loop was kind of set up for you, that's kind of how we did that with that example. If some complicated condition is true, set this exit loop variable to true, and then every time through the loop, check that exit loop value versus worrying about doing that computation itself inside the while block, inside the while statement itself. Let's do a problem-solving exercise. We can do this one together. This is a very kind of textbook example. We'll do it relatively quickly, but we'll use our process and we'll see how it applies to this. So input, unsigned integer representing a maximum value. Output, and usually when these are specified, we have to read this very carefully. The sum of all, well, even read the typo, the sum of all the even valued terms in the Fibonacci sequence that are less than that maximum value. So if you need to know the Fibonacci sequence, we generate a term. We start with the first two values are 1 and 1, or 0 and 1, but either way is fine. 1 and 1, and then the next term is equal to the sum of the previous two terms. You've probably seen it, but just in case, previous two terms are 1 and 1, the next term is 1 plus 1 equals 2. Previous two terms are 1 and 2, the next term is 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8, etc. So this is a little bit different than just calculating the terms in the Fibonacci sequence, although it generally would require us to calculate the terms in the Fibonacci sequence. It is to take the sum, calculate the sum of all the even valued terms that are less than a maximum value. Just a very slight tweak on the Fibonacci problem. So that's our goal for today. Calculate the sum of all the even number terms that are less than a max value. So as part of our problem specification, it usually is most helpful to start with what are our inputs and what are our outputs. And again, you may look at what I wrote here and say, well, that's obvious. It's very clear what the input and output is. It still makes sense to kind of write that down. What are my key necessary variables going to be? Calculate the sum of all the even number terms that are less than a max value. So what is my input going to be to this problem? Kind of written, but it's in between the words in that sentence of the goal. There has to be a max value. And I would say an integer representing maximum value. And we can say like, int max. Thank you. What's the output? Yep, representing the sum of the even number terms. I mean, do we have to really write all this? That are less than max. And we'd want to call that int, I don't know, sum or something like that. Okay? Problem analysis, I mean, part of that is given, that we need to make sure we understand that. The next term in the Fibonacci sequence is equal to the sum of the current term and the previous term. And with an example, so it goes 1, 1, 2, 3, 5, 8. And we'll just stop it at this. Okay. If we want to be a bit more explicit about what that means in practice, that probably means, although there's different ways one can implement that, there's a next term, a current term, and a previous term. I would see some value in having int next cur prev, defined in my code likely. Right? You could have done it differently or define those variables via some different name, but we need to have some way of storing that. There's maybe a little bit of a trick to that we have to kind of think about, that whether we figure this out as we're coding it up or we do it beforehand as we're analyzing the problem. Once we've calculated the next term, once we've calculated next, then eventually what was current is next, and what was previous is current, and we have to probably do that in right order. There's like not quite a swapping operation, but more of like a sliding window kind of operation, right? We've calculated what was next, but it's no longer next. Once we've calculated it, now it's the current value, and we have to calculate the next, and so forth. I have a small visualization on that of using a while loop to do that. We have previous, we have current, we're calculating next, we've calculated next, and we got to kind of slide things over. Previous and current, calculate the next. It's a little bit misaligned, but conceptually that's what we're doing there. Repeat until next is, we said less, so greater or equal to max. And since we wrote that, we can probably just put that all there, even syntactically. Until while next is greater and equal to max. And then there's one final thing in our analysis here. We only want the even numbered terms. We've used a couple techniques already to kind of calculate that. How do we calculate if something's even or not? We can use remainder too, right? So if, I guess if we're calculating next, if next mod 2 equals 0, then it's even. Then the term is even. That's just a trick, if we want to think of it as a trick. We divide by 2, and if it has a remainder of 0. We also could have done the bitwise AND operator, would have given you something very similar. AND it with the value of 1, and if the result is 0, that means that least significant bit is 0, and consequently it's even. Either approach is fine. This is a very classic approach to determine if something is even or not. We divide by 2, if there's no remainder, it's a multiple of 2, it's an even value. And with that, we kind of have our implementation, or at least the basics of our implementation. We have then defined 5 variables. We do have to read in that value of max. 1, 2, 3, 4, 5 variables. We have a while loop that we're checking for the values of next. And then we're adding it to sum if that's the case. Let's give it a try. Okay. So that was int max, sum, next, previous, and current. Our printf, scanf kind of prompt needs to say something like Enter in a max value with a scanf for that value. We have our while loop, right? Our while loop was while next is greater than or equal to max. We want to do this until next is greater than or equal to max. So we talk about bugs and or either infinite loops or loops that don't loop at all. We want to go until the value we've calculated is greater than or equal to max. So the note is okay. We want to repeat until, so I should really phrase this correctly. So that's a logic bug. Repeat until next is greater than or equal to max. So that would be more like while next is less than max, is what that equivalent would be in our code. And if you get that wrong, you run the code, the loop never executes, and you find your bug and you go from there. We're going to repeat until next is greater than or equal to max. We have a little bit of a problem here that hopefully your spider sense is tingling already that we've added a bug before we've added anything else here. Our code is going to execute. It's going to initialize max, but what doesn't it do? Yeah, there's nothing in next yet. And because of that kind of sliding window, we should probably initialize everything, right? Sum is the value we're going to keep adding to. So whether Replit kind of papers over that for us or not, we should initialize a sum variable to 0. That's a pretty good habit to get into. Next, if we assume we start with 1, 1 as our first two values, then I would set, this is just how I would do it, set next equal to 2, previous equal to 1, and current equal to 1. So while next is less than max, what do we have to do? So these things are initialized. Yeah, if we want to, so we have our current value of, or our current value of next. We have our value of next. We do have to eventually calculate the next Fibonacci value. And I think that was in our note. Well, we have to kind of slide things around, right? So previous, what was previous, we store as our current. What was current is what our current next is. And we do have to actually calculate the new value of next, which is adding up those two previous values. That sliding kind of value variables. That's a very common thing that we're kind of reusing those three variables. What was next is now the current. What was current is now the previous. And what was next now needs to be recalculated. Depending on how we define next versus current, we also have to determine if we want to add to the sum here. So like we said, we want to add to the sum if the term is even. If the term is even, add to the sum. And that was our if statement where we're checking if next mod 2 equals 0. Now we can use our little new operator, sum plus equals next. And we've done all that calculation. We should probably print it out. So the sum of the even Fibonacci numbers less than max is whatever our sum is. So less than max is equal to sum. Part of the issue with this code is I don't, off the top of my head, well, okay, we could try. If I put in 16, the result should be 10. Okay, the sum of the even Fibonacci numbers less than 16 is 10. If I put in 40, the result should be 44. And then after that, I don't feel like testing any more values at that point. So it does give us the correct result. It's not an infinite loop. It's going to loop a certain number of times. We can try all sorts of different values, and it seems to be able to calculate it reasonably quick for us, but not an easy way for us to confirm that that's actually correct. Oftentimes, once we've implemented the code, that actually works. So those are values. We're generating our sliding window, et cetera, et cetera. Oftentimes, and those are our even numbered terms, we can figure out a different approach to take. Not to say that our approach is wrong. Our approach is fine. Our approach is 100%, gets the correct score here. When looking at the even number terms, do we detect a pattern?
They have two spaces in between.
Yeah, it appears to be every third term. So that may be allow us to kind of optimize things a little bit out. We could do some interesting patterns. That's one interesting pattern that, in fact, we actually don't need to calculate every term in the Fibonacci sequence. We can only care about every third term of the Fibonacci sequence. Do we see any pattern of every third term of the Fibonacci sequence? You may not be able to, there may not be enough numbers to see it here. Assuming there was a 0 over here, like an unlabeled 0 term. What's the ratio between this term and this term? It's 1/4. Between this one and this one, it's almost 1/4, but then it's off by 2. 4 times 34, you're asking for a lot from me, 136 plus 8 is 144. Turns out, for every third term, it's 4th times the current term plus the previous term. So we could then go and refactor our code to then calculate it that way as well. That'll oftentimes be the case. Even as we go through our problem analysis steps, we can find another approach. Or f sub n equals 4 times f sub n minus 1 plus f sub n minus 2 for the even terms. Now, the question then becomes, is it worth our effort as programmers to implement that? Wouldn't be hard. What would I take out? Because that works for the even number terms, well, basically, I'd be able to take out all of this here. And similarly, in terms of initializing our values, sum is 0, we would set it up where next was now 8, previous was 0, and current is 2. And then each time through the loop, we don't have to calculate anything. We would just say, because we're guaranteed to be even, sum plus equals next, plus equals next, previous equals current, current equals next, and then next is now equal to 4 times current plus previous. So we could refactor the code. We should get the same value. We do. So, well, at least consistent with the previous version of the code. So if it was wrong before, it's equally wrong now, but it gives the same result. So that's a pretty good sign that we got that correct. Now the question becomes, which approach is better? I mean, there's different definitions of better. This is taking fewer steps. Doesn't have any if statements or mod operators or anything like that. It's iterating fewer times because we're basically calculating 1/3 the number of Fibonacci values here. It's harder to understand. I mean, so that's the other trade-off there. In someone looking at this code for the first time, maybe looking at this and say, wait, what's going on here? Why did you initialize next to 8 and previous to 0 and current to 2? Why did we multiply by 4 here? So there's like hidden knowledge that's not really even described in the code. You'd have to add probably a lot more comments to have this be understandable by someone who's looking at it for the first time. My philosophy, at least certainly, when you're not necessarily having to meet any particular performance or other constraints, is focus on readability, focus on understandability, focus on boring, get it to work. And then once you get it to work, if you're still excited to keep working on it, okay, let's keep working on it. Let's make it better. Let's improve it. That's a wonderful thing to be able to do. But do so once you already have the working version in your back pocket. Okay, I already have it working. I'm already good. I'm just excited to do more. Let's do some more for this particular program here. It's It's not really that clear to me. I mean, there's trade-offs. Which version was quote unquote better? They're different. One performs technically better than the other, but both of them are quite fast. One is, I think, a lot harder to understand in terms of visually inspecting the code than the other. That's a trade-off. It's not clearly one being better than the other. The example from the supermarket and lab is actually an example of a do while loop. It's also just referred to as a do loop. It's very similar to the standard while loop. Logically, in terms of the program flow, our control and data flow graph, the main difference is that we always execute the loop body once first. Then we have the condition that potentially loops back to do the loop body multiple times. Syntax looks a little wonky compared to, I think, the basic while loop. So sometimes it's kind of hard to justify when you have a do while versus just a while loop. So the do, that syntax is what's within the curly braces, and then the while condition is listed outside the curly braces here, and you just have to kind of get used to that syntax as being a little different. So literally, it's do it. You're guaranteed to do it once. Then you're checking whether some condition is true. If so, we're going to do it multiple times. So the difference is with a while loop, we may never do the body at all. If the first time you get to that while statement, the condition's not true, A is not or A is equal to 21 or whatever the condition was before, or next was already bigger than max or whatever our first time through the loop, we never execute the loop. That is oftentimes what we want. In this case, if we have some code in which we know that we always want to execute the body of the loop at least one time, then using the do while loop is a valid approach to have here. This is one of the examples that makes sense to me. I mean, it's not doing very much right now, which is enter numbers with some input variable here and enter in that number until you get a positive number is what this one would be calculating for you. So since you know you at least want to grab an input at least once from the user, then you could say the do while loop makes some sort of sense. But for every do while loop, you could write it as a while loop as well. There's always an equivalent program you can write that doesn't use the do while syntax. So you have to be aware of it. That's how you logically read it. No matter what, we do the printf scanf once. How many times we do it depends on what the user enters in as their input for this. So there's nothing wrong with it. It's just a different way of encoding our iterations, our looping structures in our programs. I usually don't go to it. Personally, the other approach would be have the printf scanf outside the loop, and then also have a version of it inside the loop as well. So we do it once, no matter what, then we have a regular while loop that continues to do it afterwards. This approach is fine. Another thing to watch out is floating point. We do have to use floating point in our programs. I know we've been kind of pretending it doesn't exist for a lot of the programs that we write. With our if statements, this is still an issue. It's the same issue with comparisons using floating point values, but it becomes more of an issue when then we have while loops or for loops because of this same kind of infinite looping problem that had a more blatant example previously. I think it's sufficient to say for now that we have these variables, these floats and these doubles. And just speaking of the float, that is a 32-bit variable that is meant to encode these fractional values, things like 2.718 versus just 2 or 3 or 4. And because it is a 32-bit value, there's a finite number of things we can represent with the float. And mathematically, we can represent 2 to the 32 unique floats. But in terms of fractional values, there's an infinite number of fractional values we may potentially want to have in our program. So there's always an accuracy trade-off with having these floating point formats. It's unavoidable. There's a precision issue that we can only represent values and do the arithmetic with these fractional values with a fixed amount of precision. And that trade-off is going to catch us all the time when we're actually using these float value variables to do some sort of math. Oftentimes it doesn't matter, right? Because it's going to be good enough that 2 to the 32 is a lot of values That's 4 billion unique values we can have as our floats. That's a lot. So we're probably pretty good. But it just so turns out that because of that, and we don't have to get into the actual IEEE 754 standard and how the floating point variables actually are getting stored. But because of that, there's just values that you think we can precisely represent and store in memory that we actually can't. We're approximating them. We're getting something close, but not exactly the same as those values. And with our loops, that can lead to things that logically are correct. Like you can step through every line of code and it seems reasonable, but once actually compiled and executed, will lead to a result that is a little counterintuitive and just generally a bug in our programs. This is a Taylor series expansion of Euler's formula. It's not terribly important in and of itself. If you know what that is, you're fine. If you don't know what that is, that's fine. But we can estimate e to the 1 by taking successive terms of the Taylor series expansion around the value of e to the 0 and just adding them up together. And that's what we're doing here. We're calculating an estimate. We're adding plus 1 over the denominator, and then we're calculating a loop iteration value for the denominator and multiplying it by I each time. So we get 1 factorial, then we multiply it by 2, then by 3, then by 4, then by 5 to get those successive factorial terms here. And we're taking the reciprocal of that and adding it to our estimate. It's not important. This is not an applied math class. But we're doing so, and we're trying to calculate how many iterations does it take to get a good estimate for that value of e to the 1 here. This is in code floating loop. I would say calculate e to the 1 equals f, and then I would say after %d iterations, because it's nice to know how long did it take to actually execute. And we run it. And at this point now in your debugging toolbox, I think it's sufficient to say, I hit run and nothing's happening. I mean, there could be other bad things, but infinite loop. I have infinite loop in my program. What do I do next? Absolutely. This was our do while loop. I had mentioned like adding a print statement before the loop and in the loop and after the loop. Inside the loop is fine too, right? Got here. I know that's kind of simple sounding, but that's all I really want to know. Hey, do I actually get inside my loop? It's a do while loop. I should get inside my loop, but let's do it. And we certainly got here. Sometimes those prints can be a little misleading. This one's okay. Depending on the speed of the print, it may look like it's stuck and not printing, but it actually is just printing really quickly and you can't see the refresh. In this case, we can see the refresh, and so it's clear it has got here a lot of times. Okay, that only tells us so much. What should we do next? Say it again, I'm sorry. I still can hear you.
Like sleep or the,
Pause it in between the get here's. Yes, I would say we probably want to print out the value that we're estimating, and then also slow it down. Let's do both at the same time. Calculated, either one. It's, you know what? Yeah, why overthink it? That print we have at the end is a valid debugging print, right? So just copy paste that debugging print in the middle here. I had suggested you do it without a sleep, and we're going to see real bad news. Part of the floating point standard is it allows for things that aren't numerically, quantifiable. So like infinity, negative infinity. If you ever see NaN as a printout for your float, that's not a number. That's a sign something mathematically has gone wrong in your program. In this case, we've calculated e to the 1 equals infinity after, well, I hit stop pretty quickly after 6,846 iterations. I like the idea of sleeping. One second seemed good enough with Replit to kind of see what things were looking like when we would run it. 0, 1, 2, it's getting there. Euler's method seems pretty good. We're hoping to get to E at 2.71828. Looks like it's getting there. Looks like it's there. Looks like it's there. Life is good. So why doesn't it stop? It's very close. It's probably extremely close to that value at the end of the day. And then for whatever reason, we can talk about why exactly that happens. After 34 iterations, it went from a very accurate estimate to all of a sudden it estimated the value as infinity. Any thoughts as to why it became infinity? Yeah, it is an overflow. We're taking this denominator, which is an integer, and after 34 iterations, that would mean 34 factorial. We're overflowing our integer value, not the floating point. Well, that's why it's not. That's why this condition is never evaluating to false. It's always saying that they're not equal to each other, even though visually, well, they're good enough, right? I mean, I got a pretty good estimate there, pretty decent calculation there. You can print out the float with more characters if you wanted to see it in more detail. I don't know what the limit is. We can try 8f. So give me a float, or like 1.8f. Give me a float with one, what am I trying to say here? 1 in the units digit and then 8 decimal digits in the fractional part should give us a little bit more detail in terms of what it's calculating here. And we can actually see, this is a little subtle, but that fourth iteration should be 2 2/3 is what the math would tell us it's calculating. And it kind of is 2 2/3, but it's not quite, right? Even 2 2/3 it can't represent exactly. It can give us something very close to 2 2/3, but not exactly 2 2/3. And then when trying to get to that value at the very end there, we run into the same exact bug that we had a second ago here. So there's our infinite case here. It's not going to recover from that. In general, when doing logic with floating point and using them in your if statements and in your while loops, we really shouldn't use equality checks basically for that reason. If we're doing less than or greater than, we're generally going to be okay. But equal, not equal is generally not going to work. What we want to do instead, and let me comment out this line here, or copy this line, is instead check if our value is reasonably close. Either less than or greater than we don't necessarily care about, but have we gotten to a reasonably good estimate of our value? Did we get close to the value? There's different ways mathematically to do that. You can look at absolute error, you can look at relative error. In this case, absolute error is probably good enough. We'd want to do something like take the absolute value of our estimate minus the value we want to calculate and check if it's small enough. And if it's small enough, that's a good enough estimate for our purposes. In the math.h, in the math library as part of C, generally if you can think of a math function, it exists in that and there's an absolute value. It's called fabs for reasons that are annoying, but it's fine. We want to do the absolute value of the difference of those two terms, and we should keep going while that is greater than some error tolerance. And I don't, we'd have to kind of play around with what's reasonable. Looks like it gets it down to what, right? 2.718281. Let's say 1e negative 5. So the absolute value of the difference between what we've calculated and what we're hoping to get to, keep going until it's sufficiently small. And now I think we can run this. We're assuming we've fixed the infinite loop, but we have. And we can print out the longer version of it like we did before. Let's do that here. After 9 iterations, we get a value that's not exact because it's possibly never going to be exact due to the limiting nature of our fractional values in floating point representation. But it only took 9 iterations here, or 10 depending on how you count the iterations. And we got a reasonably close result. The math does do what it's supposed to do. Let's leave things here for today. We'll talk about for loops on Wednesday. Have another quiz. I know you're looking forward to it. I certainly am. See you then.